If matrix A is equal to minus 1, 0, 1, 2, 3, 0, minus 3, 1, and 4, we are to find A to power T, that is A transpose. The transpose of matrix A is what? These are the options given to us to pick from. So anytime you are asked to find the transpose of a given matrix, all you need to do is to interchange the columns with the rows. In this matrix A, you have a square matrix. It's a matrix of order 3 by 3. That is 3 rows and 3 columns. So all you need to do here is to exchange the row. The row 1 here becomes column 1. The row 2 becomes column 2. And then the row 3 becomes column 3. That is, if A, that's matrix A, is equal to minus 1, 0, 1, 2, 3, 0, minus 3, 1, 4. A transpose will be equal to, the row 1 here will become column 1, that is minus 1, 0, 1. Row 2 here will become column 2, so we have 2, 3, 0. While row 3 will become the column 3, and that is minus 3, 1, and 4. That is A transpose. When you look at this A transpose that we have gotten, comparing this with the options, you see that option D has the same values as this A transpose. So option D is the correct option for this particular question, the transpose of matrix A. The second question here says, which of these is a diagonal matrix? Which of these is a diagonal matrix? A matrix is said to be diagonal if it contains entries on the main diagonal and zeros elsewhere. So when you look at the matrices you have here, the option that has only entries in its main diagonal and 0 elsewhere is option A. This is the diagonal of this matrix, the main diagonal, where you have entries only. The rest of this position have 0 as their entries. Whereas when you look at this option B, they have 0 entry on the main diagonal, and then they have non-zero values in other places. So the correct option is A, a matrix that has entries only in the main diagonal and zeros elsewhere. If matrix A is equal to 3, 4, minus 2 and 1, and matrix B is equal to 1, 3, 2, 1, we are to evaluate 3A minus 2B. Now, 3A is a scalar multiplication of matrix A, while 2B is a scalar multiplication of matrix B. That is, you pick 3, which is a constant, and you multiply it by matrix A. So, (3A minus 2B) is equal to 3 multiplied by matrix A, which was given to us there as 3, 4, minus 2, and 1. Then we'll subtract matrix 2B from it, and that is 2 into the matrix B was given to us as 1, 3, 2, 1. Dealing with the scalar multiplication, we are going to use this constant and multiply it by matrix A. We'll come to this one, use the constant to multiply it by matrix B. So we have 3 times 3 giving us 9. 3 times 4 giving us 12. 3 times minus 2, we have minus 6. 3 times 1, we have 3. That is, anytime you are dealing with scalar multiplication, you are using the constant to multiply each of the entries. Then we'd say minus 2 times 1, we have 2. 2 times 3, we have 6. 2 times 2, we have 4. 2 times 1, we have 2. At this point, we'll now do subtraction of a matrix. And subtraction is possible if the matrices are of the same size and shape, of which this is a 2 by 2 matrix, and we can subtract one from the other. And subtracting one from the other, we subtract the corresponding entries in each of these matrices. So what we'll have is, we are going to subtract 2 from 9. That is 9 minus 2 will give us the entry in this point. Then here will be minus 6 minus 4. Minus 6 minus 4. Then to this part we have 12 minus 6. 12 minus 6. While here we have 3 minus 2. 3 minus 2. That is equal to 9 minus 2, we have 7. 12 minus 6, we have 6. Minus 6 minus 4, we have minus 10. And here is supposed to be 2. 3 minus 2, we have 1. So this is the matrix for 3a minus 2b. And this corresponds with option D, having 7, 6, minus 10, and 1. This question says, singular matrices have A, determinant equal to 0, B, determinant less than 0, C, determinant greater than 0, D, determinant not equal to 0. Now, for a given matrix, its determinant simply is just the magnitude or the size of that matrix. So a given matrix is singular, for instance, if the determinant is equal to 0. So when you look at this matrix, for instance, matrix B, if we have 6, 3, 2, and 1, the determinant of matrix B giving us either det B or B, it's equal to, we are going to multiply this diagonal, then subtract the second diagonal from it. That is 6 times 1 minus 2 times 3. 6 times 1, we have 6. Minus 2 times 3, we also have 6. 6 minus 6 is going to give us 0. So for this matrix whose determinant is equal to 0, is said to be a singular matrix. Also, if you have matrix A to be equal to 3 minus 1 minus 12 and 4, the determinant of this matrix A will be equal to 3 times 4 minus 12 times minus 1. And that's equal to 3 times 4 is 12 minus 12 times minus 1, we have 12. And 12 minus 12, we have 0. So the determinant of this particular matrix A is equal to 0. And so this matrix is also a singular matrix. With all of this, option A become a correct option. So a singular matrix have determinant equal to 0. The next question here is, if matrix A is equal to 3, 4, 2, and 3, then the inverse of A is, here are the options. So a matrix is said to be invertible, or it has an inverse, if the determinant is not equal to 0. Remember the previous question where we looked at singular matrix. A singular matrix has its determinant equal to 0. Then a matrix is said to be invertible, or it has an inverse, if the determinant is not equal to 0. A matrix is also said to have an inverse if, when you multiply the matrix and the inverse of that matrix, it's equal to the inverse of the matrix multiplied by the matrix itself, and it's equal to identity. Inverse of a matrix can also be represented by 1 over the determinant of that matrix multiplied by the adjoint of that matrix. So in this case, 1 over det A multiplied by adjoint of A. So finding the determinant of that the above matrix, we are going to have the inverse equal to 1 over, the determinant here is going to be 3 multiplied by 3 minus 2 multiplied by 4. That is 3 times 3 minus 2 times 4. Multiplied by the adjoint. The adjoint here, we are simply going to swap the position of the entries in the main diagonal, which in this case they are 3, 3, and then change the sign of the entries in the second diagonal. So if here is negative, in the adjoint we turn it to positive. But since here they are positive, we are going to use the negative. That is the opposite. So we are going to multiply this by 3 minus 4 minus 2 and then 3. This is equal to 1 over 3 times 3 we have 9. 2 times 4 we have 8. Multiplied by 3 minus 4 minus 2 and 3. It's equal to 1 over 9 minus 8 we have 1. Multiplied by this matrix 3 minus 4 minus 2 and 3. 1 divided by 1 is 1. So multiplying the adjoint here, you have 3 minus 4 minus 2 and 3 as our final answer. So this 3 minus 4 minus 2 and 3 is the correct option, and that corresponds with option B. So the inverse of matrix A is simply 3 minus 4 minus 2 and 3. And when you look at this again, the entries in the main diagonal remains the same, while only the sign in the second diagonal changes. So option B is the correct answer for the inverse of matrix A. 2 times 1 minus the second diagonal, that is minus 3 times minus 3 times 3 minus 3 times 3. This is equal to minus 1 into 3 times 4 we have 12 minus 1 times 0, we have 0. Minus, this is supposed to be minus 0. So we have minus 0 into, I just want you to know that 0 multiplying everything here will equal to 0. Remember, we are considering this part. That is why you are seeing 0 multiplying the content here. So if we multiply this by 2 by 4, we are going to have 8. When you multiply minus 3 by 0, you are going to have 0. And bear in mind that when you multiply, everything you have here is going to multiply by 0. So the answer will still be 0. So after this step, I'm going to equate all of this to 0. So we have 8 here minus 0. And we add this to 1 into 2 times 1, we have 2, minus 9. Because minus 3 times 3 is minus 9. And that's equal to minus 1 into 12. 12 minus 0 is 12. Minus 0 times whatever you have here is equal to 0. Then plus 1 into 2 minus 9 is 2 plus 9. That's equal to minus 1 times 12, we have minus 12, plus 2 plus 9 is 11. 11 times 1, we have 11. So we have 12 plus 11, and that's equal to minus 1. With this, the correct option here is option A. If matrix A is equal to 2, 4, 6, 3, 9, 5, and matrix B is equal to 7, 1, minus 2, 9, and then 4, 3, we are to evaluate A multiplied by B. That's AB. There was one of the questions that we solved earlier where we were dealing with 3A minus 2B. That one, for us to get 3A, we use 3 to multiply matrix A. But this time around, you have a matrix multiplying another matrix. And when you are multiplying matrix, one thing that we need to take note of is the order of that matrix. Here we have a 2 by 3 matrix multiplying a 3 by 2 matrix. That is 2 rows, 3 columns multiplying 3 rows, 2 columns. It's worthy of note that multiplication of matrix is not commutative. If you have a 2 by 3 matrix multiplying a 3 by 2 matrix, the result you are going to have will be a 2 by 2 matrix. Whereas if a 3 by 2 matrix is multiplying a 2 by 3 matrix, you are going to have a 3 by 3 matrix. It means that AB is not equal to BA. If it is this 3 by 2 matrix you are using to multiply this, you are going to have a 3 by 3 matrix. But if it is this 2 by 3 matrix you are using to multiply 3 by 2 matrix, you are going to have a 2 by 2 matrix. And so A multiplying B is not equal to B multiplying A. So let's look at the question here. We have 2, 4, 6, 3, 9, 5. That is matrix A. And then matrix B, we have 7, 1, minus 2, 9, 4, and 3. AB will be equal to, we have this 2 by 3 matrix, 2, 4, 6, 3, 9, 5, multiplying 7, 1, minus 2, 9, and then 4, 3. So in multiplying these two matrices, we are going to pick a row and multiply a column to get entry for a given position. So we are going to have this first row multiplying the first column. We'll also use it to multiply the second column. Then we'll come and use the second row and multiply the first column, and also use that second row to multiply the second column. So in multiplying also, we are going to use one of the entries to multiply the next one. The second entry on this row multiply the second entry on this column. The third entry on this row will multiply the third entry on this column. So we have 2 multiplied by 7 plus 4 multiplied by minus 2 plus 6 multiplied by 4. It will give us the entry at this point. Then we're also going to use the first row to multiply the second column to get row 1, column 2. So we have 2 multiplied by 1 plus 4 multiplied by 9 plus 6 multiplied by 3. 6 multiplied by 3. To get the values in the second row, we are going to use this data to multiply first column and then second column to get the value here and then here. So we have 3 multiplied by 7, 3 times 7, plus 9 times minus 2, plus 5 times 4. Then for this side, we are going to use that same row to multiply the second column here. So that will be 3 times 1 plus 9 times 9 plus 5 times 3. So all of this, we have it here. And that's equal to 2 times 7, we have 14. 4 times minus 2, we have minus 8. So opening this bracket, we are going to have minus 8. 6 times 4, we have 24. 3 times 7, we have 21. 9 times minus 2 is minus 18. Minus 18 times positive 1, you have minus 18. Plus 5 times 4 is 20. Here we have 2 times 1 giving us 2. 4 times 9, we have 36. Plus 6 times 3, we have 18. 3 times 1 is 3. Plus 9 times 9, we have 81. Plus 5 times 3, we have 15. This is equal to 14 minus 8 is 6. 6 plus 24, we have 30. 21 minus 18 is 3. 3 plus 20, we have 23. 2 plus 36, we have 38. 38 plus 18, we have 56. 3 plus 81 is 84. 84 plus 15, we have 99. So this is a solution for AB. Matrix A multiplied by matrix B. That is 30, 56, 23, and 99. And this corresponds with option C, where we have 30, 56, 23, and 99. The next question for us is, using matrix A equal to 3, 1, 0, minus 1, minus 4, 3, 5, 4, and minus 2. We are to evaluate the minor of A11 and then find the cofactor of A12. Now, the minor of a given entry is the determinant of the submatrix that remains after the row and the column of that given entry are deleted from the given matrix. For instance, when you have A11 here, you are referring to, this is matrix A, right? Row 1, column 1. So when row 1 and column 1 are deleted, what is the determinant of the submatrix? Now, for you to find the matrix, we are making use of the 2 by 2 matrix here to find the determinant. So A11, we are deleting row 1, column 1, and the submatrix that you have left is minus 4, 3, 4, and then minus 2. So that is how to get the minor of a given matrix. For instance, you can also be asked to find A32. A32 now will be row 3, column 2. So you are deleting row 3, column 2 when it is A32. So that you are left with this and then this. So for A11, if we bring our matrix back, the given matrix A, 3, 1, 0, minus 1, minus 4, 3, 5, 4, minus 2. When we delete row 1 and then column 1, the submatrix that we have left is what? Minus 4, 3, 4, and minus 2. So the determinant of this submatrix is the A11 that we are asked to find here. And that's equal to minus 4 will multiply minus 2. That is minus 4 times minus 2 minus 4 times 3. 4 times 3. And that's equal to minus 4 times minus 2, we have 8. Minus 4 times 3, we have 12. And finally, 8 minus 12, we have minus 4. So minus 4 is the value for A11. That is the minor of A11. And that corresponds with option B. For the second part of the question that says we should find the cofactor of A12, the cofactor basically are gotten from the minors of a given matrix. For instance, if the given matrix is Aij, where I here represent the row number and J represent the column number. In this case, I is 1, J is 1. But for this second question, we are asked to find the cofactor of A12. So I there will be 1, J is equal to 2. So for you to find the cofactor of Aij, you are going to have Cij equal to minus 1 raised to the power of I plus j and multiplied by Mij. This is the minor. This minor is what we just found here for the A11 minor. So when you have the minor of a given matrix, you can now get the cofactor from it. And then another thing we need to note is the signs of cofactors. The signs of cofactor, if it is position 1, 1, you are going to have plus. The second one, minus. Here is plus. Here is minus. Here is plus. Here is minus. Here is plus. Here is minus. Here is plus. Now, how do we arrive at this? Whenever you have, for instance, Aij, if their sum gives you an even number, then that position, the value should be positive. But if the sum of I and j gives you an odd number, it means that position is negative. So what you have here, this is position 1, 1. That is, if this is a matrix A, you're going to have row 1, column 1. This is the entry in that position. And 1 plus 1 is equal to 2. So this position is equal to a positive value. Then this is row 1, column 2. That is, I in this case will be 1, j will be 2. 1 plus 2 is equal to 3. So odd number, you have a negative value. You come to this place. This is row 1, column 3. I will be 1, j will be 3. 1 plus 3 is 4. That is an even number, right? So this position is positive. You come to this place. Why is this one negative? This is row 2, column 1. So I in this case will be 2. The j, which is the column, will be 1. 2 plus 1 is equal to 3. That is still an odd number. So that's how the signs of these cofactors are assigned to these various entries of a given matrix. So we can say that the cofactor of a given matrix is equal to plus or minus the minor of that matrix. So that when the sum of I and j is positive, we now multiply the positive times the minor. If the position is negative, we multiply it by whatever value we got as the minor of that particular entry. So that is how cofactors are gotten. For this particular question, where we have A12, first of all, we need to get the minor of A12. Minor of A12. So we have A12 equal to the matrix. Again, let's bring it back. We have 3, 1, 0, minus 1, minus 4, and 3. While here is 5, 4, and minus 2. So if we are looking at A12, it means we are dealing with row 1 and column 2. So if we delete row 1, column 2, what we are left with is minus 1 and 3. Minus 1 and 3 in the first row. Then we have 5 and minus 2 in the second row. So finding the determinant of this particular entry, you are going to have minus 1 times minus 2. Then we'll subtract 5 times 3 from it. That is in the second diagonal. And that's equal to minus 1 times minus 2, we have 2. Minus 5 times 3, we have 15. So that 2 minus 15, we have minus 13. When we look at the position of 1, 2, right? So we are going to have C12 now, because we have found A12, that is a minor of that matrix, to be minus 13. So C12 now will be equal to, let's get to know what is the sign of the cofactor that should be used for the entry 1, 2. 1, 2 here refers to row 1, column 2. So the sign for the cofactor there is negative. So we are going to have the negative of M12. And M12 here has been found to be minus 13. So it's going to be minus multiplied by minus 13. Minus times minus will give us plus. And so we have 13 as the cofactor of A12. The cofactor of A12 in this particular equation is 13. You can also be asked to find the cofactor of A33, A32, as the case may be. So for each of these entries, you can apply the same method and find their entries, the cofactor and their minors. But remember that for you to get a cofactor, you are making use of the minor. Plus or minus the minor of a given entry gives you the cofactor. Lastly on this for now, invertible matrices have A, determinant equal to 0, B, determinant less than 0, C, determinant greater than 0, and D, determinant not equal to 0. Invertible matrices. Remember why we were looking at singular matrices? We did say that a singular matrix is a matrix whose determinant is equal to 0. And because of that, it is not invertible. It means that it does not have an inverse. So for this particular question, a matrix is only invertible if the determinant is not equal to 0. Once the determinant of that matrix is equal to 0, that is a singular matrix. So the correct option here is option D. Invertible matrices have determinant not equal to 0. You can follow us on this channel, Excel Victory Academy, for more of this interesting content. Thank you.